So, as I mentioned in the last class, that I shall once again work out the problem where I shall show how to expand the S matrix. So let us write down the formula for the S matrix, and that we have already derived this getting. So what I shall do is I shall set h bar equal to 1 from the beginning. Okay? And then this is basically h I x equal to x. This is the time ordered product of this exponential. And as you know that this is basically an operator, the interaction picture. This is the formula for the S matrix, and you can expand it immediately. So this will be, if you expand it, you will get so d4 x, d4 y, d x, y, and so on. So this is the expansion of the exponential series, and then first term is identity. Next term, there is only one operator. So here, let me write down what the form of HIX is. HIX is lambda by 4 factorial by 4 x. So if you substitute HIX, there are string of 4 operators, 4 pi operators. What I'm not writing it anymore. You can actually partition, write it in this form. This is the zeroth term, this is the identity. So I just write it in this form. S2 and so on. So S0 denotes this identity. S1 denotes this term, the time ordered product of this term. S2 denotes this term, and so on. So this is the expansion of this S matrix. And now what we shall do is we shall calculate the following amplitude. So we take only one particle and take this as the in state. The particle with momentum p, this is the in state, and this is the out state, particle with momentum q. So particle comes and gets scattered due to the self interaction, and we want to calculate this probability amplitude or scattering amplitude for the scattering process. This is what we want to calculate, and we have seen that you can write this thing in the following way. This is basically Q S matrix so this operator, you can write it in the following way: S infinity to minus infinity. And then this is P. This is the in state and this is the out state. The in and out states are eigenstates of the full Hamiltonian, and they are time independent eigenstates. And this is these P and Q. These are basically eigenstates of the only the free part of the Hamiltonian, and they are related in the following way. So you know this form, you know the form of this operator. You know what these P and Qs are because you can write this in the following way. Q, you can write it as AQ. Then you have S infinity minus infinity, and P is nothing but A dagger P is vacuum, and this is vacuum. So P you can create by acting the creation operator on the free vacuum. And similarly for this bar Q, you can write it as bar 0 AQ. So this is what you need to calculate, and you have the expression for AC infinity minus infinity. Just put it there. If you put it there, what we shall get is the following. So let me go to the other side of the board. So the scheduling amplitude therefore becomes AQ, this time order product. So you can write this as S0 plus S1 plus S2 dot and A dagger P in the free vacuum. This is equal to first term is identity. Therefore, this is AQ, A dagger P. This is the first term. The second term is S1. S1 is time order product of this thing. So what we can do is we can take minus I outside, we have the integral outside, then you have before x, then we have time order product of EQ. You also have this lambda by 4 factorial outside. Then you have 5 to the power of 4, x, a dagger p. So this term is the second term. And then we have the third term, basically 1 by 2 factorial. Then we have lambda by 4 factorial whole square. Then we have d4x, d4y. And so on. Therefore, you can write this as A0 plus A1 plus A2 . What you can do is you can keep this time ordering, since it is there in all the terms. You can just write on time ordering. So the terms are like this. Is this clear? Is this expansion clear?
Yes, sir.
So you can now see the full board. So let me drop this portion out. From here, let us look at E0. The term E0. It has a time order product, but there is no time here, so you can get rid of that term, the time ordering thing. So you will have AQ, A dagger P, this. And what is the value for this expression? How will you compute this? It is very easy to compute. You just replace it with the commutator because the other term is 0 as the annihilation operator annihilates the vacuum, and therefore this just gives us delta 3 Q minus P. So yeah, Q. So these are basically Q and P. This. So the first term is this. So you see that the particle without this is the leading term, is not interesting. There is no interactions, it just comes and it goes away. And why do you have this delta function? It tells you that the momentum must be conserved. Otherwise, this term will not give you any contribution. If the momentum is not conserved, then this is, if Q is not equal to P, this term is 0. So this term contributes only when Q is equal to P, which tells you that momentum is conserved. The interesting term comes from the second term. A1, A2, these are all interesting terms. So let us look at A1 now. What is A1? A1 is basically the time ordered product. I will zoom it in a second. Let me just write down the expression for it. So it is time ordered product of minus I lambda by 4 factorial integral. I'm not writing the limits because the limits are from minus infinity to plus infinity. So it is d4 x So this is the second term, and this is at first order in perturbation theory. So you take only the coupling constant to linear order. This is a linear order term in the coupling constant. Next you will get the quadratic term in the coupling constant and so on, second order term and so on. So if you look at this term, what we can do is we can rewrite this thing as this. And take the integral outside, then this will become AQ. There is phi x. As I have been telling you repeatedly, that all these operators are in the interaction picture. Therefore, they evolve. They are like free fields. They evolve via the free Hamiltonian. And therefore, you can apply the Week's theorem here. So this is what we need to calculate. Earlier, what we have done, if you remember, we were calculating the propagator, where the particle propagates in the interacting vacuum, and it was a different kind of calculation. There you didn't have these operators, but now this is a different calculation. You are looking at a scattering process where you have these operators. So let's see how we can proceed from here. So now we have to apply Week's theorem. So this is the point where we need to apply Week's theorem. Can you see the board now?
Yes, sir.
So this is A1, and A1 is this. And since all these are free fields, this is the free vacuum, the state of minimum energy of the free part of the Hamiltonian. So you can apply Week's theorem here, and here you can see that there will be two kinds of terms. One where you contract A with A and you contract phi amongst each other. So this is one kind of term that you will get, and the other is where you contract A's with phi's. So A you contract with one of the phi's, and A dagger B you contract with one of the phi's. So there are two kinds of terms that you will get from this by using the Week's theorem. What about the term where we contract A with A and phi's with phi's? there will be three kinds. Actually, when you contract it, you will see that a factor of 3 arises, because there are 3 ways of doing this contraction. And so I will write it over here. If you contract this, the time ordered product of AQ phi x, there are 4 phi x's here. And you need to calculate this. So you can contract these. Then these are the only 2 ways. So you can contract this. So this is a contraction of A with A, and now you contract the phi's. And you can contract the phi's. There are 3 possibilities in which you can contract, and each of these possibilities will give rise to the following result. It will give you a factor of 3, since there are 3 ways of contracting these phi's, and therefore you will get a Q, A dagger P. See, this for this term, you don't need to put the time ordering because there is no time here. So this is just this thing, and then you will get. So when you contract these 2 phi's, there are only 2 phi's left. So it will be a product of 2 vacuum expectation values. It will be something like this: phi x, this. So that is equal to 3. Now this is once again the Dirac delta function, 3-dimensional Dirac delta function, Q minus T, which tells you that the momentum must be conserved, and this is nothing but phi x contraction, phi x contraction. So these are the propagators, T propagators. Therefore, we have built T delta Q minus T I delta F x minus x and I delta F. So these are the Feynman propagators. So the result of contracting the A's with A's and phi's among themselves gives rise to this term. But there is another possibility where you contract the A's with phi's, this A with one of the phi's and this A dagger with one of the phi's. So when you contract A with phi, suppose you take this one, you contract this with this, and you contract this with this, there will be a term where you need to contract the 2 phi's also. So this will be the other kind of term that you get from this Wick's expansion. And you can check for yourself that there are actually 12 ways of doing this contraction. So once you do the contraction, you will get a factor of 12 in front. So for this kind of contraction, we will get 12. Then we will have, so let me just write it in this way: AQ phi x contraction, phi x contraction. So this is the Feynman propagator, and phi x is A dagger P contraction. This contraction basically means that it is the vacuum expectation value of phi x with A dagger P. And you don't need to take the time ordering here for this term because there is only one time. This A dagger P does not have any time, so you can forget about it. Okay? Is this clear?
Yes.
Okay. So let us do this calculation. See, this you already know. What is this term? This is I delta F x minus x. But this contraction and these contraction, these are not contractions among phi's. These are contractions among A's. This is a mixed type of a contraction. It is a contraction between a field phi at x and the creation operator or the annihilation operator. So we need to figure out what this this contraction means.
Sir,
Ah,
why we are not summing these two results together in the A1 value?
we will sum it.
Okay,
Once we calculate this, then we will write down the full result. It will be a sum of both the terms.
okay, sir.
So let us take this contraction phi x with a dagger p. So this actually means that this is a vacuum expectation value of phi x and a dagger p. This contraction basically means this. How can you calculate this? It is very simple. Put in the mode expansion of phi x. So you can put it. It is basically d cubed a by 2 pi whole cube 2 omega k square root. See here, you only need to keep the a term, not the a dagger term, because then the a dagger term, if you keep the a dagger term here, it will be two a daggers, and therefore that term will be 0, right? Therefore, we just have so this of I a dot x, and then like 0 a k a dagger t. But as I said, the a dagger term will vanish. Now this, you know what it is? It is basically delta 3 k minus p. Therefore, you can perform this k integral, and you will get 1 by. So this is the value of this contraction. What else? I call this factor in front as NP. So this contraction is basically NP to the power of minus IP dot x, where NP is this factor in the front. And similarly, I leave it as an exercise for you to do at home to calculate this term, AQ with phi of x. Here you need to keep the a dagger term in the mode expansion. So you calculate this term. If you calculate it, you will get the following result. AQ with I of x contraction. This is nothing but a vacuum expectation value, and this will give us NQ, where NQ is again is the normalization factor that I discussed just now. This will give you NQ e to the power of I Q dot x. Instead of minus I, now you will get a plus I. Because a dagger from here contributes, and that actually brings the plus IQ dot x on top of the exponential. So now you have calculated both these contractions, and you know what this is, and therefore you can plug it. You can actually put it over here. So A1 therefore becomes minus I lambda by 4 factorial integration d4x. And then you have this thing, but this thing is basically this term. You can write it as 3 delta P minus Q I x. So that is what you will get from there. And then you will get plus 12. So this gives us np in q to the power of minus I minus q dot x. Then we have I dot x minus x. X minus x, that is basically delta f of 0. So this is the result, full result for A1. And you can similarly go on, proceed, and try to calculate what A2 is. But for the time being, we shall concentrate on this term that we calculated just now. We shall concentrate on A1. Is this okay? Is this clear?
Yes, sir.
Good. Let us look at this term, the first term, and try to draw a Feynman diagram for this term. So, what is the basic vertex? The basic vertex is this. This is an integration over x. Okay? And whenever you see a vertex, what you do is you put a minus I lambda factor and you integrate over that point before x. So this is the basic rule for this vertex. Put in a factor of minus I lambda and you have an integration over that point before x. So you can see why it is like that, because this A1 is a term calculated up to first order in the coupling constant, first order in the perturbation theory. Therefore, it has only one vertex, and for one vertex, you can see there is an integration over d4x. Okay. Next, what do we have? We have this thing, the momentum conserving delta function. So it basically means that, so this actually arises, this delta 3 PQ is nothing but the contraction of AP and A dagger Q, right? Because this is nothing but the vacuum expectation value of AP, A dagger Q, HC. This gives us delta 3 P minus Q. So this term is nothing but the contraction of AP and A dagger Q, the Dirac delta function. So it is basically nothing but you can draw it. You can draw this term the following way. The particle is just coming and going. There is nothing very interesting that is happening. So you can, so this line basically tells you, gives you contraction of a P, a dagger Q. So this is the vacuum expectation value, and then you have this I delta x minus x. So this is the diagram that we have already seen. Because this is delta f 0, but the 0 is centered at the vertex x. So you have two blobs here at the point x. And you can see from this the first term is basically nothing but a disconnected Feynman diagram. It is a disconnected Feynman diagram. Okay? Let us now look at this second term. Let us look at this term, this 12, this.
Sir, the delta term we are keeping in the contraction form itself in the diagram.
Yes, the Dirac delta is basically this contraction. So it is something like this. So what I'm saying is that I'm just representing this contraction AP a dagger Q by this line. So the particle is coming and it is coming with momentum P and going away. And then you have another piece which is a block like this.
But sir, earlier you
Yes,
hello.
please. Yes.
But sir, earlier you when you defined the straight line diagram, there you said that that is some kind of function I delta of x1 minus x2. But here it is delta also.
This is just okay. If you don't like this, you can say okay, I will draw it like this. It's just a pictorial way of understanding the thing. Okay. The pictorial, nice pictorial way of understanding. So the particle is coming like this and it's going away. And these I think is compatible with the thing that I mentioned earlier to you. Let us look at the second term, this term, and try to simplify this term a little bit more. So this term is basically integral E4x I'm just leaving out the factor of 12 and things like that. So we have already calculated this. So this is NP NQ e to the power of minus I e minus Q x, then I have I delta F. Okay. This you can write it down as you can pull out these NPs and NQs outside because these are constant numbers and you have d4x over this integral. This is independent of x. So this will give you a delta, again a Dirac delta function. You will get delta 4, you get a factor of 2 pi whole 2 pi to the power of 4, delta 4, p minus q from this, and then you have I delta 0. This delta 0 you can write it in an integral form like d4k by k square minus m square plus I u c. This actually is this expression. I delta 0 is this. The exponential is 1 over here. So once again you can see the momentum conservation is there. So the expression for that term is this. Now let us try to draw a Feynman diagram. So as I mentioned that this is the vertex. And now you can see that there are two contractions, phi with a dagger and a with phi and phi with phi. So these are the four legs, these are four phi's kind of. You have four phi's here. Okay? And phi contracting with a dagger, it is something like this. So it gives you a dagger basically it is responsible for creating a particle. Therefore, you just extend this leg. So once you have this contraction, this term is actually responsible for giving you this e to the power of minus I p dot x term, right? So what happens is after this contraction, you get something like this. I've just elongated this tail here. This elongation of the tail actually denotes this contraction of phi with a dagger. Then you have this phi contraction. So this is the contraction of two phi's. This is contracted like this. So what do you get at this moment? You get something like this. Get something like this. And then you have A with phi. So you elongate this part, and then you get something like this. So this part represents something phi x a dagger t contraction, the phi contraction, and this part is A with phi contraction. So this is how you get this kind of a diagram. And so it is in this direction that time flows. You can just rotate it and you can write this as so what this basically means is that the particle with momentum p comes like this. This is the direction of time flow and it goes away with momentum p. And there is a loop momentum p. This loop arises because there is an integration over x. There is a vertex, therefore there is an integration. There is a loop here. See, now you can see that this is delta f0. So this is a loop integral over k, right? So this is the loop that you get, delta f0. Delta f0, I told you that gives you the loop. So for that you can see that there is an integration over k. So now what you get is the diagram corresponding to this expression, this 12, all these things. So this is the diagram corresponding to this expression. So this is how you can actually get a feeling for about how these Feynman diagrams can come into the picture. And we shall see later that actually we have already done it, that whenever we have a straight line, we associate it with a propagator, and the propagator has an expression. Whenever we have delta f0, it basically means that there is an integration over k, and so on. The vertex, we have to replace it by minus I, and then there is an integration over the x coordinate. If you have two vertices, there will be two integrations over x coordinates, and this is how you make sense of these Feynman diagrams. So from this term, you can immediately see that there is one vertex here. There are four lines in this vertex. There is a loop. The loop has a momentum k, and this is the momentum of the incoming particle. This is the momentum of the outgoing particle. This is a connected diagram that you get. So it is from the second term, this term that you get a connected Feynman diagram. From the other part, you get a disconnected Feynman diagram. And you, as I mentioned earlier, that you can actually forget about the disconnected Feynman diagram. So you see that here, what we have done, this expression was initially an expression where integration over x's were there, but now this expression has converted to an expression where there is no x. You have integrated out the x. The x has been integrated out, and this full term that you had in this expansion is now an expression in momentum. So just as we had Feynman rules in position space, you have Feynman rules in momentum space also. And therefore, if I ask you that I give you this diagram and tell you what is the value of this diagram, actually you have already derived the Feynman rule for this diagram, because you have a vertex. So vertex means you have to put in a factor of minus I lambda. But now the rules are in momentum space. So what you do is that there is a vertex, momentum is coming in, momentum is going out. Therefore, there will be a momentum conserving delta function, P minus Q. There are two external legs. This is an external leg, this is an external leg. Particle is coming in and is going out. Two external legs. Legs correspond to these factors of NQ and NP and NQ. These are the normalization factors that you have for each of the external legs. So whenever you have an external leg, you attach a factor of NP. So there are two external legs. One leg is with momentum P, so you attach a factor of NP. The outgoing leg has momentum Q, so you attach a factor of NQ, multiply them. This 2 pi whole to the power of 4 delta 4 Dirac delta function comes because of the momentum conserving delta function. Because of momentum conservation, so since there must be momentum conservation at each vertex, therefore you must have this factor, Dirac delta function factor. And since there is a loop here, there must be a loop momentum, and each loop actually corresponds. You know that it is I delta F0, and therefore each loop actually corresponds to this integration over the loop momentum, which is nothing but d4k by this. So you have a loop momentum, and it is I delta f, the Feynman propagator x minus x, that is 0. Therefore, you have I integral d4k k square minus x square plus I epsilon. There is no factor of e to the power of minus I k x minus x is 0, so that exponential is 0. Exponential is 1. And therefore, for this diagram, there are two legs. So each leg actually, in momentum space, each leg, if this leg has momentum p, this corresponds to a factor of np. Each vertex, this is in momentum space, everything is in momentum space. Each vertex will give you a factor of minus I lambda. And also, not only that, we will have 2 pi whole to the power of 4, delta 4, momentum conserving delta function. So you attach this factor, and since there is a loop, you put in a loop integral over k. So these are the Feynman rules for phi-4 theory in momentum space. But let us pause here for today. I think this is already a lot of material for you to study. You go back home, look at what we have done. The basic takeaway lesson for today is that we have expanded the S matrix and we have tried to calculate its scattering amplitude where a single particle comes in and scatters away. And we have done it in the context of lambda phi-4 theory. It's a real scalar field theory and it has an interaction of lambda phi-4. We have written down the scattering amplitude of the first order in perturbation theory and tried to grind each of the terms using Wick's theorem. Once we have done that, now we try to make sense of those terms in terms of simple diagrams, which are known as Feynman diagrams. And another thing that we have done is the following. We have taken one of these terms, we have taken this term, and we have tried to what we have done is we have taken this second term and we have tried to write down, or we have tried to simplify this expression or simplify this integral over x in terms of an integral over k, or simplify this full expression in terms of momentum. We have taken this expression. This expression was in terms of x's and these contractions between aq and phi x. We have now converted this expression in terms of momentum. And in the process, we have obtained, for the second term, we have obtained an expression like this. You can similarly obtain an expression in terms of momentum for this diagram also. I leave it as an exercise for you to do. But from the second term itself, you can actually derive what the Feynman rules are. You can this term actually corresponds to this diagram where the external leg corresponds to the normalization factors of NPs. Each vertex will give you a factor of minus I lambda together with a factor of together with a Dirac delta function because of momentum conservation, for momentum conservation, and there's a loop. The loop is coming because you have a I delta of 0, and therefore this loop actually corresponds to this integral over k. So there, since when you have a loop momentum, and therefore there is an integration over the loop momentum. So if there are two loops, there will be two integrations, and so on. There is one loop, there is one integration over momentum. So what we have done is we have converted everything. Earlier we were doing things in terms of in position space, but now we have converted everything in terms of momentum. We have taken things to the momentum space, and just as we had Feynman rules in position space, in configuration space, now we have Feynman rules in momentum space. And in the next class, we shall elaborate on this aspect in more details. What we shall do is we shall compute the second order term also. This is the first order term. We shall compute the second order term and try to write to see what are the possible Feynman diagrams and what are the expressions for what are the mathematical expressions corresponding to those diagrams, and can we use the Feynman rules to write down the expressions corresponding to those diagrams. So this we shall do in the next class. So do you have any questions at this point?
Sir, don't we need arrows for the disconnected diagram? Just the line, momentum
Forget about
conservation.
this term is not interesting. Just look at this term. This is the interesting term.
Okay.
Forget about that term. I showed you one example, no, where we calculated the propagator. That was the first example.
Yes.
Where calculated the propagator. There we had a disconnected piece and we had a connected piece. And I told you that you can forget about the disconnected diagrams because that will not contribute to your scattering. That will not contribute to the propagator. That will not contribute to the correlation functions. That will not contribute to the propagator, to the scattering process also, scattering amplitudes. So you can forget about it. The interesting term comes from the second term, and this gives you this diagram. This diagram we also encountered in that example, in the propagator problem.
Yes, sir.
You remember this diagram?
Yes, sir.
So we encountered that diagram there also. Here also we encountered same thing. But there we were doing in terms of we were writing down Feynman rules or Feynman diagrams in positions. If the Feynman rules were in terms of were in the position space. Okay. But now here the things have changed. Things are different. Remember that propagator that we wrote down, the example that we showed, that was a 2-point correlation function that is in position space. So there were 2 points in x phi x1, phi x2 time order product, vacuum expectation value. Vacuum is the interacting vacuum, the full vacuum of the theory. So there were 2 x's. So in the final result, then if you write down a diagram, that actually corresponds to 2 x's. So when you write down a propagator, this propagator you are drawing, so there will be 2 points. Those are x's. Okay? Because x1, x2 has not been integrated out. They are like free indices in tensor calculus. So x1, x2 is not integrated out. So there are 2 points, x1, x2. But here you can see that we are trying to calculate this a1. X has been integrated out. What is left? The Q's and P's are like the free indices. So the final result that you have, so all these diagrams that you will have here, these are diagrams in the momentum space. Now you realize the difference between the two.
Yes, sir.
This diagram, when we drew it, when we were calculating the full propagator of the 5-fold theory, propagator connected up to first order in perturbation theory, the two ends, the 2 points here were x1 and x2. x1, x2 plus x1, x2 with one loop correction plus and so on. But this diagram is something different. It tells you that these 2 points are like, these are not x1 and x2 because there is no x1, x2 here. It's an integration over x. There is no x here. You will integrate the x throughout. X is gone. Whatever remains is, and the fact that x is gone can be seen from this final expression. This expression corresponds to this thing, and this expression has no x in it. Why? Because x has been integrated out. A1 does not have any x, so is A2, so is A3, and so on. There will be no x. But what will A1 depend on? It will depend on the external momenta, the values of the external momenta. You are shooting into particles. One has a momentum p, and one has a momentum q, and then they are scattering and they are going away. So the results, the amplitudes will be momentum dependent. And so this diagram is a Feynman diagram in momentum space, not in position space. And therefore, you need to calculate Feynman diagrams. You need to derive Feynman rules in momentum space. And we have actually derived the Feynman rules in momentum space. Is it okay?
Yes.
Good. So let us finish it here. All of you, I hope, have submitted their answer scripts in Google Classroom.
Yes, sir.
For their mid-semester exam.
Yes, sir.
So, okay, good. So let us end the meeting here today. Let us stop here. We'll continue in the next class.